Okay, hey everybody, welcome back. Tonight we're going to talk about soils, especially pertaining to viticulture and vineyards. So, a little overview of today's lecture. We're going to have an introduction, then we're going to talk about the differences between soil profile, soil composition, and soil texture. We're also going to discuss water holding capacity, like how soil can hold water for plants to use and utilize, and then we're also going to talk about water infiltration and drainage. So just a very tip of the iceberg for soil. There's a lot more that we will discuss when we get into like cation exchange and minerals and fertilizer and stuff like that, nutrients. But for today, we're just going to talk about the basics of understanding soil health, and why it's important in viticulture, but just in growing in agriculture in general. So, introduction, important aspects of the soil. So, really important things that we look at. One of the most important things is field holding capacity and drainage. So, the amount of water that soil can hold, and also how the ability to drain that soil. Roots will get waterlogged, the soil will rot. It's a host of living microorganisms and soil pests, and a place for roots to thrive for different systems of plants. So the ability to hold water but also drain is a very delicate balance. And this is determined by soil texture and also the organic composition of soil. So soil texture is the relative amounts of sand, silt, and clay particles in soil. We've talked about that in a previous lecture. So that's the texture. Then we have organic composition. This is the fraction of soil that consists of decomposing plant and animal tissues. That'll be very important for like the water holding, but also for nutrients and so on. Then we also have soil profile. A soil profile are the layers formed through weathering and time. So there's kind of just an overview of some of the different aspects of soil. So starting with part 1, soil profile. Soil profile are the layers formed through weathering and time, like we just said. If you dig deep enough in any soil, you will see layers, also known as horizons. Once you put those horizons together, you create a soil profile. And it's very diverse soil profiles. You go from county to county, from vineyard site to vineyard site, or even within vineyard sites. There's lots of variation in soil. It just depends on a lot of things like erosion, or if there was previously a river there, or if it was based off of volcanic materials or other parts. So it varies a lot, and this is why people who plant vineyards will dig very large holes to understand the soil that they're working with and see if it will be a suitable area for vines to thrive. So it's very important. So check out the soil profile and horizons. We have soil organic matter, also known as SOM, S-O-M. This becomes humus as it decomposes. So you see humus, that's related to that. So a little bit of a breakdown on these horizons. We have the O horizon, which is our organic layer, O for organic, so humus organic. This is mostly organic matter, such as decomposing leaves. So, if you have a yard that with plants and trees, the leaves will fall off those trees or shrubs, and then you'll typically get a layer of decomposing leaves in the fall. It's very pretty, but there's also a point to that decomposition provides nutrients to worms and bugs and to roots and all these other wonderful things. So that is our O layer. Directly beneath that, we have the A layer, which is topsoil. So this is mostly minerals from parent material with organic matter incorporated. It's a good material for plants and organisms to live. This is also known as the zone of leaching because things leach into this zone. So O and A, these layers are easily moved by wind and water erosion. They're very prevalent in the foothills and valleys, not so much like on the tops of mountains, right? Because as water moves down the mountain, it pushes the soil down. So you have more of this at the foothills and valleys than you would at the top of mountains. So that is important to know. Also important to know, these top 2 layers contain the most life in the soil, the most biota, so all of the worms and fungi and all the things that will thrive in these 2 layers of soil. It's a very healthy, rich part of soil. So that is important to know. Moving on to horizons B, C, and R. So next we have the B horizon, which is subsoil. This is rich in minerals that leach down from A or E. E is not on this chart. Most charts don't talk about E. We're not going to talk about E in this class, but E is kind of like a hybrid layer between these two sometimes. So B, subsoil, is also known as the zone of accumulation, which is just kind of an interesting component about that. Then as we move down to C, the parent material, this is weathered bedrock. This is the deposited earth's surface from which the soil develops. So this is kind of like the parent material. This is like an unconsolidated layer that, as it wore, eventually created the B layer, and then the A and O layer got placed on top of that. And then R is the bedrock, and this is a mass of rock. It's not soil. It's very important to remember this is not soil. This is solid rock, such as granite, basalt, quartzite, limestone, or sandstone. And this forms the parent material for some soils. And this is located under the C horizon. So once you hit bedrock, there's not really much you can do as a builder or as a viticulturist. So the bedrock is the bedrock, and that's just the bottom of your horizon. Cool. So how different horizons are made. Horizons are created by erosion and organic matter incorporation. So younger soils are typically created by tectonic plate activity and volcanic eruptions. We have tectonic plate activity every day, of course, and also like volcanic eruptions under the ocean, and also on top on land too, right? So this will create new mountains and land. These are typically shallower soils. Then we also have older soils. Those are deeper, and those have been in the making for millions of years. Cool. So examples of poor versus well-drained soils. We talk about these horizons, and what these horizons contain will affect how well your soil drains. So here on this left side of this image, we have our R horizon, which is just consolidated rock, right? And then we have a C horizon, and then some exposed R, and then we have some root system up here, but it's very shallow and it cannot penetrate the C horizon. So this is parent material that we're seeing here. Then we see as this rock has been weathered, and as it's moved down through wind and water and erosion, it's developed a very thick A horizon, and this is becomes very water saturated. This is high in nutrients. You see a lot of plants thriving down here, and this is also just the natural flow of water, so there's plenty of space for those roots to grow, but also water for them to thrive. And then here we have more horizons, and you can see we have larger trees on this hillside that can grow. So very different situations in draining of soils. Cool. So young soils with shallow horizons have lower water infiltration than older, deeper soils. So younger soils, shallow horizons, right? So you get to the bedrock, that very bottom horizon, much faster. There's less space for roots to grow, but there's also less ability for water to infiltrate or to penetrate through the soil, right? So it's going to be very difficult. So in the Sierra foothills, there's lots of variation in soil horizon depths, and that's because the topsoil and all the erosion that came off of the mountains. So we get some of that from the erosion, but also we're in a very strange and unique situation because our county has a lot of history, in just the Sierra foothills in general, have a large history of hydraulic mining. So that's when they would take a ultra powered water hose and just carve into the mountainside. So we had lots of erosion from that, and so lots of soil has been spread across the whole county and the whole Sierra foothills because of that. So sites will differ, but it just depends. So the big takeaway is shallow soils have less water infiltration and limited growth for roots. It becomes very difficult, right? And here we have a couple different examples of soil horizons and kind of composition across different regions. So this first one we have, looks like we have clay, lots of clay, and this is from Sacramento near Clarksburg. And we have a clay loam, straight to metamorphic rock. So the roots can only penetrate so far until they hit straight rock. And this is in Auburn near Jamestown. And then this last one we have Redding, and this is gravelly loam soil, and this is near Clements, California. Sorry, this might just be Redding gravelly loam. That might be the name of the soil, is Redding. But anyways, you can see how far the roots have penetrated through these different horizons. You can see the different change in color of the different soil types, and how it's weathered over time. So lots of variation. If you're going to think about establishing a vineyard on your property, it's very good to dig a very deep hole and do some analysis. And there's other testing you can do too, that we'll talk about in a couple of slides. Cool. So soil composition. What is soil composed of? Well, there's 4 major parts. Number 1, the highest composition is mineral fragments. So this is dislodged from the parent rock through weathering over time. So you have a solid piece of rock that gets hit with wind and water and just wear and tear, and it starts to break down into smaller and smaller pieces. Those are mineral fragments. Then next is air, which might be surprising. But there's pores in soil, and if you look at it under a microscope, it's actually, there is space for air. It's not just a solid piece of rock, right? All of those different pores and different sizes of fragments of things, there's air in the soil too. This is very necessary for cellular respiration of most living organisms, so absolutely necessary for the health of soil. Then we have water, which is about 25%, and then organic matter, so both alive and decaying organisms. Those are all very important. So that's soil composition. Soil texture is determined by the composition of rock particles. So there's only 3 types, right? We have sand, which is the largest, silt, and clay. So texture is defined on what percentage of these items exist. So we've seen this before. This is a texture chart or texture table, and you would determine your soil texture by finding out the percentage of each type of component are in your soil sample. So a soil that contains 15% sand, 15% clay, and 70% silt would be silt loam, right? So let's start off with sand. We have 15%, so right about this way, sand, 15% clay. Okay. And and 70% silt. So you would, we're around here. You can make a mark on your chart right here and just draw a line up, and then 15% here, draw it across, and then 70% you could draw a line down, or you could follow this diagonal, and you would be in the silt loam section of that chart. So that's how you'd find out your soil texture classification. Cool. So how would you do this, right? Seems like it'd be very complicated. No, it's actually not complicated. It's very fun. You just grab a jar of dirt, and then you would fill it with water and add just like a drop of soap. The soap is just going to make sure that all those particles get saturated with water. You'd actually grind up your sample first, that way there's no clods or chunks, that way all of the particles can separate. Then you could measure, they'll separate the 3 different components. You'll measure it on this graduated ruler side, and then you can calculate your percentages. Then you can refer back to this chart and determine your soil texture. So very cool, straightforward procedure. We will do this in lab, so feel free to bring a jar of dirt from home. It's gonna be a good time. Cool. Water holding capacity, part 4. So water holding capacity is very important because our roots need access to water. They also need access to oxygen and nutrients and a host of all sorts of wonderful things. But your soil texture and your organic matter in the soil will determine your water holding capacity. That's very important. Why is this important in a grand scheme of things? Well, you might have some house plants that show some stress, and so that is your indicator to water them. But when you run a vineyard operation in a business, you don't want to use too little water, and you don't want to use too much water because you'd be wasting money with a massive bill at the end of the month. And so it's important to know where the sweet spot is for that, right? So we use this lovely chart here, and on the x-axis down here we can see the different soil textures have different abilities to hold on to water. So sand has the least amount of water capacity to it at all. Sand will just water drains right through it, and that's it. Clay has the highest ability to attract water, and that's because the particles are so fine, it stays within the pores of that. The sand, it just falls right through, and then loam is somewhere in between. So depending on your texture, you could find out your field capacity, and then that is the maximum of what your soil can hold for water. And then once it reaches below a certain point, that's your permanent wilting point, there's zero water available for your plant. So this is why we don't need to water every day. We water within a certain period of time. So there's a general relationship between those things. And this is in inches of water per foot of soil depth. Cool. Field capacity and wilting point. So field capacity, kind of like we discussed, the water reaches, penetrates through the soil, and then it adheres to the soil. That is kind of like saturation. Saturation, you add the water, the pores are full of water, and water is actually draining through this system, and all gravitational water is lost. Field capacity is what, after the excess drains, what the soil retains in it, that moisture is what's available for plant growth. Plants don't just drink very quickly from a straw and feel good. They accumulate nutrients and water slowly through the soil, so it needs to be held in place in the soil for them to obtain it. Once all of that field capacity is used up, either through the plant, through evaporation, or some other force, then there's zero water left in the pores of the soil, and that is the wilting point. So no water is available to the plant becomes stressed, and then it starts to wilt. So that is not a good time. So deeper soils will retain water longer than shallow soils will. So you just have more of a bank to pull from if you have deeper soils, right? If you have shallow soils, then you don't have a lot to work with. Soils with high organic matter concentrations will also retain more water for a longer time. So the comparison to this, when I looked up organic matter retaining water, is that organic matter is very porous on its own, and so it acts like a sponge for holding water as well. So organic matter is very beneficial for multiple reasons. Then we have texture versus structure. So texture, like the little triangle chart we saw, is the relative parts of sand, silt, and clay. So this will affect your soil air, your water retention, the tilth, and is also associated with the fertility of the soil in general. Structure is a little bit different. It refers to the aggregation of soil particles into larger units, right? So also known as PEDs. So you can think of it as that little water test up here. There it is, right? So if soil existed like this on its own, like it was just a bunch of particles put together, it wouldn't be very helpful. It wouldn't be beneficial to plants. We need to have structures so there's an ability for for roots to grab onto things, for roots to search through tunnels that have been created, and so forth. So structure is extremely important and is an indication of health of a soil overall. So these aggregation of soil particles and PEDs, they can be small or granular, or large and in various shapes, including platy, blocky, and columnar, so shaped like a column. Their structure type, size, shape, and grade influence soil permeability to air, water, and roots. So they just form lots of textures and tunnels and little alleyways for water and air and roots to penetrate and feel their way around the soil. So it's very important. So soil structure is an important indication of healthy soils. So aggregates create soil structure, and so therefore aggregates are an indication of health, right? So how do aggregates form? They form naturally, natural forces, so wetting and drying alternatively can create kind of lumps and aggregations in soil. Also, organic substances derived from root exudates. So roots will secrete these substances that create aggregates around them as well. It's very natural, happens all the time. Roots themselves, so roots just pushing through the earth and moving soil below it will create aggregates. Then we also have fungi, which is very cool, which produce something called glomalin. It's an organic substance that glues soil particles together into aggregates. So that's this wonderful picture that you see here. So if you've ever been to like a garden center and pulled out a potted plant and seen all this little white stuff, this is glomalin. You can find it in like the topsoil where you have a lot of decomposing organic matter. That fungi loves that. So you'll see a lot of that white stuff. And it actually used to freak me out as a kid, but now that I know what it is, I think that's really cool. Earthworms and other soil animals will also help create aggregates because they allow channels that allow gas exchange and also provide a space for roots to explore. So roots don't have eyes, so they use feeling sensors to kind of look for water and find where they need to travel to. So very important. So structure of soil determines the ability for water to drain. And ... I'll find out what that word was supposed to be. So more on soil aggregate stability. If you'd like to read more about this, I have the Ohio State University extension linked to this presentation. It was a very cool write-up. I enjoyed it very much, so you can check it out if you would like. So here's a really good picture of why soil aggregation is so important. So it's important that we have these aggregates because otherwise soil just falls apart and it causes erosion, right? So there's no structure to soil, then there's nothing saying that a strong wind or a strong flow of water would just blow everything away, right? And just like demolish everything, expose your roots, and it would be a very sad day. So we have a picture here of, on the left, a beautiful soil aggregate, and on the right, soil that is not aggregated. So it says here, healthy soils are held together by soil glues or glomalin that are produced by fungi. Soils rich in soil biota hold together, while soils devoid of soil life, say that 5 times fast, fall apart and form a layer of sediment in the bottom of the jar. Pictured above, the soil on the left is from a field that has been managed using no-till for several years. The soil on the right is from a conventionally tilled field. So no-till would allow those 2 top layers of that horizon to be very rich in biota and structure, right? All those aggregates. Tilling is going to break apart those aggregates in that soil, and you're going to get a lot of erosion, and that's why we have this soil that's falling apart in this picture. So, again, just reinforcing. The gluing of soil helps to maintain pores and channels in the soil for air and water to enter and move through it. It's very important that it can move through it because roots need oxygen as well as water. Otherwise, you get waterlogged, and that's how your roots start to rot. So, aggregation affects soil water capacity and drainage. Soil aggregates are more stable and harder to wash away than individual soil particles during rainstorms. Soil aggregation is an indication of health via soil structure. So I know, kind of a little repetitive, but hopefully a light bulb goes off and you guys kind of get the big picture of why this is so important. So here we have an image of a well-structured soil, and B, a poorly structured soil. As you can see, a well-structured soil has large pores, and for the ability of air and water and nutrients to move through the pores. It's very important. A poorly structured soil is very small pores. Water pools and remains near the surface. Air has a very difficult time to enter the soil. Water and nutrients move very slowly. Air may be excluded. So not a good time. The soil and roots need to breathe as well. Cool. So how do we measure, or how do we, find out if our soil has large pores or small pores, or if it's available to grow plants healthily? So water infiltration is the measurement of water passing through soil. So it needs to pass through, and it needs to pass through it at a reasonable rate and not just pool at the top. Otherwise, it's a sign of compaction, right? So when water touches the soil, it does one of two things. It either enters the soil, which is infiltration, or it runs off the surface, right? And that's runoff. Compaction could cause runoff. And so compaction is when soils don't have very little pores, and it's very tightly bound together. It's very compacted. So this is difficult, makes it difficult for percolation and evaporation. Runoff leads to erosion and flooding. Not great. It's also difficult for your roots to find their way through the soils and to establish themselves. So all around, a very bad situation. Less disturbed soils generally have more pore space, less runoff, and are just generally healthier for plants. So the less that we till and dig and ruin those rich top layers of soil, the better off everything is. Cool. So talking about texture and infiltration, bulk density is a very important component of this. So bulk density is going to measure the rate or the degree of soil compaction or lack of porosity that you might have on a site, right? So a soil with less organic matter will have less aggregates. A lack of soil structure, aka aggregates, will mean less pores, right? Less pores, high density soil. Very high density, not a lot of pores, high density, which also leads to high instance of compaction. So not a lot of water flow, not a lot of air, not ideal for plants. So if you want to measure bulk density, you take the weight of your soil sample, you subtract it from your dry soil sample, divide it by the volume of sample as it exists on the ground, and that will give you grams per centimeters cubed, right? So then we have here a table, the general relationship of soil bulk density to root growth based on soil texture. So it gives you a range depending on your texture, right? And it gives you an ideal bulk density for plant growth. So if you're sandy, it needs to be below 1.60, but it cannot be above 1.80. So that is your range for health for that. And then for silt and clay, it gives you those numbers as well. So a really nice way for you to tell without dropping hundreds of thousands or millions of dollars on planting all these vines, for potential for a business, whether or not this is going to be successful or not. Or if you're going to have to do some serious work to farm the soil before you can farm the grapes, right? Very important, very important. Soil compaction, not ideal, right? So it's the process of these soil particles being pressed together, reducing pore space, and creating a very problematic, non-ideal environment for our roots. So we have a decrease in water infiltration, right? Because the pores are so tight, the water is having a hard time crossing through the space. It limits your root development and scavenging for nutrients and water, so your plants are going to struggle, and they won't live for a long time either because they need to establish healthy roots. It also imposes unnecessary drought and nutrient stress on the vines. It will reduce your vine growth and also the healthy microbial activity. If there's compaction, the vine's not going to do well, and also the whole biota of the soil is not going to be happy either. So they're not going to be able to help each other and flourish. Also, it increases superficial flooding and more erosion, of course. So we're just going to keep moving this topsoil around. You can see the flooding here where the vehicles or tractors have driven through the vineyard multiple times. The weight of those tractors are compacting the soil, and so that's why you're seeing that even though they might have just had a rain, all of the soil is puddled at the surface because of that compaction, but you don't see any puddles right here next to the vines because no one is driving on that space or walking on that space. So there are some videos online about the beauty of using horses and like donkeys in vineyards still, because it leads to less compaction. Stepping on the same path over and over again will create compaction, but maybe it's just less offensive than a farming vehicle. I'm not sure, but just food for thought. So where does the water go? So water, whether it's precipitation, rain, or irrigation, right? It will do a couple of things, right? It percolates down to the water table via gravity. That's drainage. It'll just run through all the different soil types to the water table, whatever path that is, and that's drainage. It can also be released back into the atmosphere through something called evapotranspiration, right? And that is just a very fancy word of two words put together, and that's evaporation and transpiration. So transpiration happens as plants photosynthesize, right? And they can release water that evaporates from either the soil or the surface. Any water that is held in the soil, which is the field capacity, right? So after the gravity has taken the drainage, whatever stays in the soil is field capacity. That is either available for the plant to consume, but also for evapotranspiration as well. So that could be evaporating from the top on very hot days. That's also why we get a lot of humidity under the canopy during hot days, because the soil is evaporating moisture, and so that's how you get all of that humidity under a canopy. If you've ever noticed that working in a vineyard, that's where all that part of that moisture is coming from, and also from the plant itself. Cool. So measuring drainage, we have two things. We have a bulk density and an infiltration test. I'm just going to add this here. Boom. All right. So bulk density is a measure of the density of the soil, right? So we kind of talked about smaller pores equals higher density and lower infiltration. Larger pores, lower density, higher rate of infiltration. So this is an indicator of soil compaction and can be used to determine soil structure, porosity, and permeability. So the bulk density test, we take a sample and we look at the components, right? Then we have the infiltration test. And this is a test of how quickly water passes through the soil, so how quickly it infiltrates, right? So as soil moisture levels increase, your infiltration rates decrease. As soils become wet, infiltration rate slows to a steady rate, right? Based on how fast water can move through the most restrictive layer, such as a compacted layer or a layer of dense clay. So it's important that you saturate your soil to its field capacity, and then you start measuring the rate of infiltration after that, because then you'll get the true drainage. If the soil is very dry, it just needs to the water goes to two places, right? It fills the bank of the field capacity, and then it starts draining. So to determine infiltration, you'll have to fill the bank first of field capacity before you can see the actual infiltration rate. So this is very helpful to predict erosion and also determine soil health. So very, very important. Okay, so those are our student learning objectives. Definitely review these before you take the quiz. I hope that this was helpful for you guys. Definitely feel free to review that. There are links in the slides for additional learning if you'd like to utilize those. Don't be shy, and if you have questions, we can also talk about it in class. Alrighty, hope you guys have a good day, and I will see you next time.